Good. So now we have to go a little bit deeper into such kind of things. So black boxes, two-port networks, as they are properly called, with an input and an output, and something that connects the input to the output, a model. So now we have the simplest possible model, which is this. It's just a constant. We read it like this: the output equals G multiplied the input. So let's consider this now. We consider the input as a sinusoidal, and we want to know what's the output when we make use of linear components. And what we are seeking for is such kind of relation where the output would be something multiplied the input, but this time this something will depend on the frequency omega. So we call this thing transfer function. A of omega is called transfer function. So in order to be able to describe this object, we write the input like this. So we make use of the Fourier transforms. We have a voltage which is varying in time, the input. We compute the Fourier transform, and for each omega we get a number. We call this number V of omega. And similarly we do for the output. So this A is simply the ratio between the Fourier transform of the output, which we call V out of omega, and the Fourier transform of the input, which we call V in of omega. And now what we will study, it's a more simple case, which is the case where this transfer function A, that in principle can be any function, can be expressed as the ratio of two polynomials. Then we made this substitution as equal I omega. So this is the numerator and this is the denominator. It can be. It's not something that a priori should be like this. We just want to focus our attention on this type of transfer function that can be written like this. So just to introduce a nomenclature, if we write this numerator n of s and we set it equal to 0, and similarly for the denominator, then we obtain two equations, and we can find the solutions of those equations, which are called the roots of the polynomial, and the roots of the numerator are called zeros, the values of the variable for which the polynomial, if you compute this summation, equals 0. And for the same thing, if we do this for the denominator, those solutions are called poles. And there is also another definition, which is called the order of let's say this transfer function, which is the maximum number between n and m. So the maximum order of the polynomial, we call it the order of the transfer function. So order is the max between m and n. So why we want to study such kind of transfer functions like this? Because it turns out, we don't demonstrate this, that when you assemble circuits made of lumped elements, which means discrete components connected together, so a network of components connected together, then the transfer function is always a rational number. So a ratio between those two polynomials. So this is a very useful condition. It means that if we go in a shop and we assemble a thing like this, then the transfer function comes in this form, and this will simplify a lot the study of it. There is also another representation, not through the transfer function, but through another thing which is called K, the kernel. And the kernel is defined through an operation which is indicated with this big star, not to be confused with the little star that we use for the complex conjugation operation. And this thing is called convolution. And it corresponds to this operation written here. I don't want to go into the details of this, but I just want to because we will not use this in this course, but I will just want to mention that this kind of object, kernel, and this kind of operation, convolution, it's something that you might meet when you will speak about transfer function of things that are called filters. And there is a relation between this K object and the transfer function of a function of a filter, and the relation is this one. So it can be demonstrated that the kernel is the inverse Fourier transform of the transfer function. So you can describe such kind of a linear circuit in two ways, with the transfer function or with the kernel. It's the same because they are connected by this relation. In this course we will use this, the transfer function. Okay, now we silently introduced the word filter. What does it mean? So if you have an idea of a mechanical filter, like this kind of grid we had in the kindergarten to filter the sand, so it's something that makes something passing through and something not. So now, with this idea in mind, we study circuits that has an input and an output, and will make some frequency passing from the input to the output, but some others will not pass. So what does it mean? If you remember, when we did the frequency synthesis of a square wave, we said that the signal can be represented as a summation of many sinusoidal frequencies. And now we want to analyze circuits that can suppress or enhance some frequency components in order to modify the signal in a so-called frequency domain. So we can do different type of filters, but before we go into the filters, we have to go to the blackboard and analyze one very simple but important circuit, which is called the voltage divider. So now we study the voltage divider. So the voltage divider is a circuit where we have a battery, one resistor, and another resistor like this, and we want to be able to calculate the voltage between these two nodes A and B. R1, R2. So first of all, this is a schematic diagram, so we can rearrange the components in a different way. The circuit we will obtain will be the same of this one if we just keep the connection. So if the so-called netlist, if the will stay the same, if the topology of the circuit is the same, it doesn't matter. For instance, if I put the resistor R1 instead of putting it here as it is, I can put it also here. It's the same. It's connected the same way. So first we can realize that this circuit is this one. It's a two-port network done this way. So I do this because these are not wires, these are just the boundaries of a black box that we consider. So here we have the input and there we have the output. R1, R2 is the same circuit. So therefore there should be something like a transfer function for these things, because it's a circuit made of lumped elements and they are linear, they are resistors. Okay, so let's calculate the output. Now I call this thing V output and this thing V input. This is very simple because I can simplify this circuit like this. So I have a battery, then I put the equivalent resistor, which is just the summation of the two resistors because they are in series, and then therefore the current I flowing in this circuit, if this voltage is V input, is simply the result of the Ohm's law applied to this equivalent resistor. So it's V input divided R1 plus R2. And then this is the same current flowing in this circuit. It's an equivalent circuit. So specifically the current I is flowing also into the resistor R2, and then we can apply the Ohm's law to the resistor R2 in order to get the voltage across it. So V R2, which for us is V output, equals the current I, so V input divided R1 plus R2 multiplied R2. And if I write it better, I do it with a different color, you obtain that the output is equal the input multiplied R2 over R1 plus R2. So this is another thing that is good to remember forever, as the Ohm's law and also as the parallel and series circuit, because it turns to be very useful, and now we will see an application of this. The application is the study of this circuit, which we call the low-pass filter. So notice that it is a voltage divider, but it's made of one resistor and one capacitor. So we can use the formalism that we have studied right now, the phasors, in order to study this circuit. So I go back to the blackboard. And now we have this. R, C. Here we have the output. Here we have the input. And I transform this circuit into this one. Okay. So now, in place of the resistor and capacitor, I put two little black boxes, which are the symbols for the impedance, and I call this ZR and this ZC, the impedance of the capacitor and the impedance of the resistor. So the output would be the input multiplied a transfer function, which is like this. So it's the voltage divider we have calculated so far, but now with impedances. Now it's simple because I just have to remember the definition of impedances. So the one of the capacitor was 1 over I omega C, and the one of the resistor was R, or we can say 1 over SC if we put S equals I omega. So I can substitute those two things inside this equation. And so I get that the output is the input multiplied 1 over SC divided by R plus 1 over SC, which I can write it also like this. I multiply the numerator and the denominator of this big fraction by SC, so nothing changes, the invariant property of multiplication. So it's 1 over 1 plus SRC, and this is equal to the output, which means that the output as a function of omega, or if you prefer as a function of S, but let's write it like this, is just 1 over 1 plus SRC, and this thing is what we call A of omega. So those two things are the Fourier transform of the output and the input, which is what is written here. Okay. So here we have our A of omega. So we may notice that because this thing is a proportion between the input and the output, so the input is measured in volts and the output is measured also in volts, it means that the units of A is nothing, is unitless, it's a pure number. So this thing is a pure number, divided a pure number, plus this thing which is a pure number, but S is I omega, and omega is a frequency. The frequency has a units of 1 over seconds, radians per second. which means that in the transfer function a equals 1 over 1 plus src, this thing as the unit of a time. So it's a time. I call it tau. So tau equals rc. And 1 over tau is a frequency, omega 0, which is called cutoff frequency. This. So if we carefully study this function, a of omega, it's a complex number. It means that we can compute the magnitude of a of omega and also the phase of a of omega, sometimes indicated with this angle thing like this. Let's call it phi of omega, and this one is the magnitude. So if we plot the magnitude of this function in a logarithmic scale, then it's like this. It's flat, and then there is a turning point around this omega 0 cutoff frequency, after which the magnitude of this guy is starting to getting smaller and smaller and smaller and smaller and smaller. So this result just comes from studying the magnitude of this function. So roughly, we don't do this, but if s equals I omega, the bigger the omega, the bigger the denominator. So you are dividing 1 by a number that becomes bigger and bigger and bigger and bigger and bigger, which means that this thing is becoming smaller and smaller and smaller and smaller and smaller, which is what is written here in the graph. Okay, so this thing is called low pass filter because if you apply a signal here having a representation in terms of Fourier, so you have a signal with is the superposition of many frequency components. At the output you don't find all of them to equally pass. The ones which have a higher frequency will be attenuated more and more as the frequency of those components is big. So this thing is useful, for instance, now I go back to the blackboard. This thing is useful, for instance, when you have a signal like this. I draw a chart. So here you have time, and here you have a signal, let's call it f of t. A signal like this. So this signal could be decomposed into a big signal like this, plus a small but fast signal like this. If you add dot by dot those two things in a graphical way, you will have something like this. So we might want to say that in this context, this is our signal of interest, and this one is something we can call noise. If we start from such kind of signal and our goal is to recover this beautiful smooth signal, out of this noise, then we can make use of a low pass filter. So we put our noisy signal as the input of a low pass filter, and then we recover our smooth signal like this. So this is the first application of a circuit that do something in the frequency domain. It removes frequency components which are not interesting for us. Okay, so let's go back here. So I want to emphasize a couple of points. So first is that this thing is a transfer function. It means that it's a complex function. So there is a magnitude and a phase. So this thing is not one thing, it's two things, a magnitude and a phase. Most of the time it's interesting to study only the magnitude, but sometimes also the phase is interesting. Then another thing is that we solved this circuit in the frequency domain involving transfer functions, Fourier transform, and all these things without computing a single integral. So this formalism transforms differential equations into algebraic equations, which are very simple to be calculated. We just calculated a ratio here. So it's a very good formalism to study such kind of circuits because it's easy to calculate. We don't have to solve complicated calculations. So then here we have another thing which is the so-called high-pass filter. It's a complementary circuit, complementary to the low-pass filter. It's done this way. So now the two-port network is like this. First we have a capacitor, then we have a resistor. By following the same logic, we can analyze this voltage divider by considering the impedances of the components, and then we will arrive to this result. And if we compute the magnitude of this thing and we plot the magnitude of this, then we will have this time this plot in a logarithmic scale. Those plots are sometimes also called Bode diagrams. Bode diagrams. More specifically, the Bode diagrams are the so-called asymptotic plots. So the approximation of those curves with pieces of straight lines. And again here we have a cutoff frequency omega 0. So now this circuit, if we apply this circuit to the noisy signal we had before, so to this one, okay. Oops. So the high pass filter applied to this signal, instead of giving us as output the smooth underline slow signal, will give us as output the opposite. So it's like this. It will give us the noise. Why it's like this? Because if we look at the representation of its transfer function, the transfer function in this case is suppressing the low frequencies, so the value of its magnitude is very low for omega, very low, and it's high for high frequencies. So in case we have a high frequency noise, the circuit will make that noise passing out, passing at the output. Then there is also another type of circuit. It's a combination of a low pass and high pass filter. It's called the band pass filter. We don't study this in the details, but we just comment the chart of its magnitude, the chart of the magnitude of its transfer function. So the bandpass filter is something like this. It suppresses the frequencies before a certain omega 0, then those frequencies between a certain omega 1 will be transferred to the output, and then again it suppresses the frequencies after this omega 1. So the game of the circuit design is to be able to find the components that will produce such kind of transfer function for given omega 0 and omega 1. So we want to design the filter, which means to find the components that can implement this feature. And this can be done with such kind of analysis. Then another important filter is the so-called notch filter, which makes everything passing from the input to the output, unless a very narrow band, ideally one frequency, centered around a certain value omega 0. So here you have an example of very complicated things that you can do just with few components, and those are very useful in order to implement so-called signal conditioning, which means to try to modify your signal according to the specification you want.